A special case is for gas phase equilibrium when all the substances involved in the equilibrium are gases. We can define a regular concentration-based equilibrium constant between the concentrations of the reactants to the concentration of the products. However, because we usually prefer to quantify the amount of gases using pressures, we can define another pressure-based equilibrium constant for gas phase equilibrium, which is a ratio between the pressure of the products to the pressure of the reactants. And it's in most cases, these two equilibrium constants are not going to be equal. They're actually related to each other for any gas phase reaction using this formula right here, where the pressure-based equilibrium constant equals the concentration-based equilibrium constant times RT to the power of delta N, where delta N is the change in number of moles of the gas during the course of the reaction. It's basically the difference between the number of moles of the products and the number of moles of the reactants. That's an example here for this reaction. The concentration-based equilibrium constant equals 10.5 at 220 degrees Celsius, and it's asking to calculate the value for the pressure-based equilibrium constant. And you just substitute in the formula with the universal gas constant times temperature in Kelvin, which is going to be 493 Kelvin. And the power is going to be the change in number of moles, which is the number of moles of the products, 1, minus the total of the number of moles, or the sum of the number of moles of the reactants, which is 3. So the change in number of moles is -2. So you plug in the numbers and you get the pressure-based equilibrium constant. And as you can see, it's significantly different from the concentration-based equilibrium constant. Another parameters that we can use to affect equilibrium reactions according to Le Châtelier's principle is change the amount of substances in the equilibrium using volume or pressure of those substances or gases. So whenever you increase the pressure, the equilibrium will shift to the direction with lower number of moles. So in this example reaction here, products are lower number of moles, 1 mole of products in comparison to 2 moles of reactants. So the equilibrium is expected to shift to the right-hand side in this case. If you decrease the pressure, it's going to be the opposite. It's going to shift itself towards the more number of moles. So it's going to shift itself to the left-hand side. And same thing for volume. When you increase the volume, it's gonna shift itself to the direction with the more number of moles. So increase volume is gonna shift to the left-hand side in this example here. If you decrease the volume, it's gonna be the opposite. It's gonna favor or shift itself to the right-hand side to the less number of moles in the reaction medium. The second parameter that you can use to affect an equilibrium reaction is temperature. And that is gonna depend on the nature of the reaction, because depending whether the reaction is an exothermic reaction or an endothermic reaction, is gonna be different. Because in this case, heat or energy is one of the ingredients in the reaction. So if you're reacting A to make B, and that reaction produces an amount of heat, whatever affects this amount of heat is gonna affect the equilibrium of the reaction. If you increase the temperature of the reaction medium, that is gonna be actually adding energy or heat to the reaction. And according to Le Châtelier's principle, the equilibrium is going to shift in the direction that offsets that change. So it's going to go backward in this case. So if you increase temperature, if it's an exothermic reaction, the reaction equilibrium constant itself is going to decrease because it's going to shift backward to offset the change or the increase in the temperature. If that is an endothermic reaction, is going to be the opposite, because in an endothermic reaction, energy is actually in the reactant site. So when you increase temperature, you're adding energy to the reactant site, which make the equilibrium shift to the right-hand side to offset the increase in energy, and that will increase the equilibrium constant of the reaction. If you decrease the temperature, it's gonna be the opposite. It's gonna increase the equilibrium constant for exothermic reactions and decrease the equilibrium constant for endothermic reactions. So that's an example for an endothermic reaction. So it's actually basically you have to add that amount of energy here. So when you increase the temperature, you're adding heat to this side, so it's gonna cause the reaction to go to this direction or have more nitrogen dioxide in the medium. When you decrease the temperature, you're actually removing heat out, so the reaction is gonna shift to the left-hand side and have N2O4 in the medium, and that's the case when you have the reaction at colder temperature. It's going to be mainly N2O4 in the medium, and when you put it in a hot medium, it's going to be mainly NO2 in the reaction medium. The last parameter that affects equilibrium according to the Châtelier's principle is the catalyst. But the catalyst does not affect the magnitude of the equilibrium constant, and it also does not shift the position of the equilibrium in the system. It will just make the system reach equilibrium faster. So basically, that's a comparison between an uncatalyzed reaction versus a catalyzed reaction. It's basically gonna decrease the magnitude of the energy barrier that is needed for the reaction to proceed. So the reaction is going to need less energy to proceed in both directions, because if you compare the activation energy needed for a regular reaction with the activation energy needed for the activated reaction, is going to be smaller, which will make both the reaction in the forward direction and in the backward direction proceed faster. And if you remember, equilibrium constant is a ratio between the reaction in the forward direction to the reaction in the backward direction. If both of these increase equally, the ratio will still be the same. So the equilibrium constant will not change. So just to summarize, these are all the parameters that you can use to affect an equilibrium reaction. And these are the expected effect of each of them on the equilibrium position itself. Both concentration, pressure, and volume and temperature will shift the position of equilibrium for a reaction. Adding a catalyst will not. It's just going to make the system reach equilibrium faster. And only temperature is going to affect the magnitude of the equilibrium constant itself, depending on the nature of the reaction, whether it's endothermic or exothermic.